Welcome to Lesson 12C, Canopy Hoods. We're going to continue talking about hoods. We're talking about now canopy hoods used for buoyant plumes. The word canopy implies that it's above, and that's exactly what it is. We have canopy hoods that deal with surges and spillover. We're going to talk about that, how to avoid it. Here's the definition of a canopy hood: a funnel-shaped hood positioned above a process, designed to collect buoyant emissions such as dust, fumes, vapors, or mists. Some examples: metal furnaces, where you have melting metals that give off fumes, welding fumes, steel mills, etc. Any process that produces smoke, or it could be vapors or mists, etc., that are hot and they rise. Here's a table or something, and we have some kind of a source that's producing smoke or mist, etc. I should have actually said smoke up here because that's one of the main things. Fumes and smoke are similar. So what we do is we have a canopy hood that looks something like this. Here's the face. It's a funnel-shaped hood, and you've seen these in labs and stuff. And so the idea is that you draw out flow through the hood, and as we know, because of the candle effect, it's going to come from all sides like this and go into that hood, and the idea is to capture all that smoke. Obviously, the funnel has to be a little bit bigger than your source. Sometimes you can't do this. So for example, the pickling example I had before, where you were taking plates of copper and sticking them from overhead into a vat of acid, you could not have a canopy hood there because that would interfere with the crane above. That's why we had a lateral hood for that case. If it's just a steady flow, it's a normal design like before. But what's interesting is when there are surges. So we're going to talk about how to design these for surges. If this is the canopy hood, we're going to define some volume in here, VH equal the volume of the hood. And then we have our source that's producing smoke. So a surge is when, say there's nothing going on, then suddenly you're doing some process and you get a whole bunch of smoke. Okay, and that process lasts for some time and then it stops. That's called a surge. A limited time source. For some time, we'll call it TS typically. The source is on for some time, TS. And so what happens is the smoke will build up. Meanwhile, you're drawing out, we're going to call that QW here, the withdrawal. People use different notations for different kinds of hoods. So typically they use a QW, the withdrawal rate. Typically that's constant. But you don't need that to be so huge that you just sucked all this smoke out right away. The smoke starts building up. And what can happen is some of that smoke can build up and then start leaking out the sides. This is called spillover or spillage. Those are the two terms that are commonly used. I like the term spillover better because it's more descriptive. You have to have two things to avoid spillover. You need Q hood big enough to handle the source, the smoke, and you need VH big enough to avoid spillover during the surge. You have to have both of these met in order to have a proper design. So obviously, if there's a lot of smoke and you have a small flow rate, no matter how big your hood is, eventually it's going to fill with smoke and you're not able to draw the smoke out fast enough, so it's going to spill over. On the other hand, you may have enough volume flow rate on average, but if your hood doesn't have a big enough volume, it'll start spilling over before this thing shuts off. Once this source quits, you have all this smoke that can slowly be drawn out, so you have to have a big enough volume as well. Here's some pictures. This is in a steel mill, the one on the left there. You can see all that smoke coming up. There's a rectangular canopy hood up there that would go out, either out the roof or to some cleaner. Here's a fancy kitchen hood, and they're pouring some oil on something that's burning, and you get smoke, and the idea is to draw that smoke out. Here's a picture with spillover. We have a range hood and smoke, and it's coming out over the edge. I like this picture so much, I put that as my main picture on this course website. How do we avoid spillover? Let's look at a typical situation that you might have. I'm going to plot volume flow rate as a function of time. You have a surge like this, and over some period it repeats. So some time later we get another surge like that, and then we get another surge later. And obviously this can have various shapes. Let's define this total volume then as Vs, that's the surge volume, we have some time period at which this happens, and we'll typically call that TS, but we're going to do this all the way to capital T, the period between surges. We're assuming that it's periodic. You can analyze this then for just one of the surges, and we assume that all the smoke's gone by the time we get to T, and then this would be 2T, and we repeat the process. We can analyze this saying that this volume, Vs, the surge volume, would be the integral from 0 to T, Qs dt. Qs would be this red curve that I drew there. This is our surge volume in a period. And since everything is periodic, we can analyze this just in that one period from 0 to T, and the goal is to avoid any of this spillover, and we remove all the smoke. If we design it right, by the time we start again, we don't have any smoke left, and then we start over. You only have to do this once. Meanwhile, you have some Q of the hood that you want to analyze, so let's call that QW somewhere here. This doesn't have to be constant, but in most of the cases, we just turn it on and it's constant. If I look at that same time period T, I can sketch the volume of the hood flow rate, the withdrawal volume, so we'll call this VW. VH is the actual hood volume, so VW is the withdrawal volume in time T. The surge volume was also in time T, but it's actually 0 anytime between the surge and up to T, so we don't have to integrate that part. So we can write a similar equation for VW, the withdrawal volume, and that would be integral 0 to T of QW dt. If QW equal constant, then VW is simply QW times T, and that's the typical case. To avoid spillover, QW must be large enough. VS is less than VH, and VS is less than VW. We're saying that the total volume of smoke or fumes, whatever's produced by this source in one surge, one period, is less than the hood volume, and the withdrawal volume, the amount of air that's withdrawn by the hood in that same time period.
Dude, why do we have to satisfy both criteria, man?
Anyone want to take a shot at this? I will, sure. I'll share my screen. Let's look at two extremes. Suppose you have a large flow rate, but a very small hood. During the surge, even though this flow rate is large, the smoke could spill over. Now consider the opposite extreme. You have a very large hood, but a small flow rate. Now the smoke will come up and be gathered inside the hood, but if the flow rate isn't big enough to draw it out in time, you'll still get spillover.
Great job, Sean. Thanks, dude.
We have to satisfy both in order to have a proper canopy hood. So here's just a summary of the equations: hood volume, source volume, QS, which is generally a function of time, QW, usually constant, and then we define VS and VW, and then here's our parameters to avoid spillover that I just had above. So that's all there is to it. Let's do a quick example. Let's look at a canopy hood. I give the hood volume. There's a source of buoyant smoke. We're withdrawing at a given flow rate, and time period is given 10 minutes between these surges. We're going to estimate the total volume of smoke that can be generated per surge without danger of hood spillover. Plot Q versus T, and let's suppose we have some kind of a surge like this with a volume Vs, and then at some period T we have another surge, and I don't really care what the shape is. It can be some kind of a rectangle, it can be rounded, whatever. It's the total volume that I'm worried about. And so we go from 0 to capital T. We just keep repeating this. And so the volume that we're interested in is this volume Vs. And then again, we have a hood, and we're going to design this hood such that in one period T, this blue shaded volume, which we call the VW, the V withdrawal, is equal. So we'll set VW equal VS at a minimum. So this is the minimum required. And in this problem, it's kind of backwards. We're given QW. We want to know how much VS there can be that you can manage with a given QW. Vs and Vw are given. Qw is a constant. Therefore, Vw equal Qw times T. As long as we can do a good job on one period, we know that we can do it forever as long as it's still periodic. And so Vs must be less than Vw. Qw was 1.50 meter cube per minute, and capital T was 10 minutes. So you see the minutes cancel and we get 15.0 meter cubed. And remember our two criteria, Vs must be less than Vh, 21.5 meter cubed. So whichever one of these is smaller, this one is smaller. And so my answer would be Vs max is 15.0 meter cubed to avoid spillover. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.